Good day, everyone. So we are happy to be to Dr. Yani Ioannou with us today. He is an assistant professor and Schulich researcher at the University of Calgary in the Department of Electrical and Software Engineering of the Schulich School of Engineering and leads the Calgary Machine Learning Lab. He was previously a postdoctoral research fellow at the Vector Institute, working with Professor Graham Taylor and a visiting researcher at Google Brain Toronto. Yani completed his PhD at the University of Cambridge in 2018, supported by Microsoft Research PhD scholarship, where he was supervised by Professor Roberto Capiola and Dr. Antonio Criminizzi. So it's great to have with us Dr. Yani, and whenever you're ready, the floor is yours. Thank you.
Great. Yeah, thank you for the introduction and thank you for the invitation. And sorry I can't be there in person. It was a little bit too, not enough time to quite get there and arrange a trip, and unfortunately teaching during the term, but I look forward to visiting in person another time. So yeah, today I'm going to talk about distillation, and distillation's got a bit more attention recently with LLMs and the more recent LLMs. But today I'll give you a little bit of a crash course through distillation and fairness, and then talk about our work in this area. But before that, just a quick introduction to myself. Yeah, so we already had a quick bio, but basically my background is machine learning and computer vision with a focus normally on neural network efficiency. And that's where the distillation side comes in. But yeah, I've had a bit of industry experience as well. And that is also what is reflected in this work, is that distillation is used a lot in industry. And it was from seeing how it was used in the industry that this work came about. So I'll talk a little bit about what my lab works on. We work on a bunch of different things around fairness, trustworthy AI, looking at reinforcement learning. But the main focus is really on the efficiency of training and inference with neural networks. And of particular interest to myself is sparse neural networks. And these are some of my students working in these different areas. Today, what we're going to be talking about is this paper, which was just recently accepted at TMLR. So TMLR is a journal in machine learning that's taken off quite a bit in the last few years. So this is not officially out yet, but it will be, like, we just made the camera ready, so it should be up within a couple of weeks, I believe. And this was also presented at NeurIPS, so the recent NeurIPS in Vancouver in December of last year. So you may have seen some of those there before. And of course, I want to mention that this work was done by Ida, who was my master's student. She just defended in January. And I'll be referencing back to that at the end. So let's talk a little bit about knowledge distillation. Knowledge distillation is not a new idea, and it has been around for a long time now. And with the success of deep learning especially, it's taken on a lot of importance, because one of the strengths of knowledge distillation is being able to take the knowledge from a larger model. It started off actually as an ensemble of models, but these days it's typically a much larger model, and distilling it or transferring that knowledge to a smaller model. So what's surprising about knowledge distillation is that when you do this, despite the student being a much smaller model, it really does seem to typically preserve your generalization or your test accuracy, if we're talking about typical classification setting. And so this is commonly used both in academia, but especially in industry, to compress large models. So typically it's much easier to develop large models that have a good performance in terms of your generalization. And then honestly, what typically happens is that in an industry, you have a pipeline typically to make a model more efficient and deployable. And distillation is just often part of that pipeline without people even potentially being aware of it. And so that's why it's important to study it. So yeah, I mean, it's used outside of areas you might expect. So you might not be surprised that distillation is used to make models more efficient for mobile applications or for embedded applications. But frankly, it just makes your model cheaper to run, and compute costs matter. When you're serving up a model at scale, like Google or Amazon or a lot of companies around the world, then those costs add up quickly, and all of that is just bottom line. So it is very pervasive, not just in the mobile space, but also any model you use. And in fact, one of the best ways to motivate your work is always to refer to whatever the latest craze is. And I'm sure most of you have heard of DeepSeek, even if you haven't heard of distillation. But the fact is, with DeepSeek itself, the models actually used in practice are these distilled models based off the base model, which is this massive 671 billion mixture of experts model. So that's really, these models, which range from 70 billion to 1.5 billion. The main way that DeepSeek came up with those models is just distillation, which is what we're going to talk about. And this is just highlighting again, it is important because this is what's used in practice. But even at the state of the art, level where we're talking about these massive LLMs, this is a very important topic. And as an aside, like I just heard Gemma 3 just came out like I think a few days ago. This is also key to a lot of the Gemma 3 models, which are much smaller. The Gemma 3 models from Google, that is. Okay, so how does knowledge distillation work and what's the intuition behind it? Because that's actually quite important for what we look at. So, hopefully you're all aware that neural networks are function approximators, right? That's why we like them. There's, a proof that in the infinite width case in a single hidden layer, a neural network should be able to represent any function. Now, in practice, of course, we're approximating those functions. And a neural network is a function just in the very simple fact that it takes an input. So, for example, X, and that X might be an image or natural language encoded in some way, and it gives you an output Y. So what we're going to be talking about in the case of distillation is mostly classification. So that classification output will typically be an output label. So very straightforward. A function, takes X, gives you Y. And yet we don't always think about neural networks this way, but it is important to think about them this way. Now, in fact, when we're using neural network for classification, the way we train it and the way that we actually use it is, it doesn't directly predict just an output class. It doesn't give you an integer of the output class index. What we typically get at the output is you get logits that's pushed through a softmax to give you a probability distribution. And we try to think of, we try to use that probability distribution to give us an idea of how confident the model is of that classification output. And typically we choose the maximum to give us the hard classification label. So that's all you need to know for where distillation came from, because distillation is actually quite an intuitive idea. And this idea came, of course, from Jeff Hinton at University of Toronto about 10 years ago, over 10 years ago now. Essentially, the idea here is that, when we train in a supervised manner, so when we have a labeled data set, we have X, your input, which might be an image, and you have the label Y, so it might be cat, dog, or airplane, as shown below. That's great. That's a lot of information. That's what we use to train a model. It turns out these models themselves tend to learn something that's much more rich than just being able to predict that label itself. They learn a rich knowledge of that domain by learning features. And if you take a model that was trained, for example, on ImageNet, which is a very large, actually, I shouldn't say very large anymore. In the current climate, it's not large. But what used to be a large image data set for computer vision, and where a lot of this progress came from, it will be trained on 1,000 different classes. Those classes include cats, dogs, and airplanes, and many other types of objects. And it will learn, sure, how to tell you whether an image is a cat or a dog or an airplane, but it also knows more than that. So it will give you this probability distribution at the end of the model. And I've just given like a very made up example here where, cat is given with a probability of 50%, and the dog is 40%, and the airplane, 10% essentially. This is just made up, but it's trying to illustrate the fact that, it knows there's more similarity between a dog and a cat, at least in terms of features, but also, implicitly, we know there's more similarity between a dog and cat than, say, a cat and an airplane. So that might not seem super useful, but it is useful, right? It's more information than we have from the labels alone. And in fact, if you're familiar with label smoothing, it's not an unrelated concept. Now, I gave that example, but in practice, neural networks are very overconfident. In practice, the actual probabilities you get out of a model would be extremely high for the class that is correct, or the class that the neural network thinks is correct, at least. So you're more likely to get something like this top example with temperature equals 1, where you get like 90% probability that it's a cat, and maybe close to 10% probability it's a dog, and then very low probability that it's anything else essentially. So although this idea is really nice that we can use the probabilities out of a model to give us more information, in practice, to make that information more prominent, we have to change the softmax that's typically used in a neural network. And this is the idea of a temperature softmax, and this is what is used in distillation, where we simply modified the softmax function, so that's at the top here, which hopefully you've all seen before. And we add this temperature parameter, so this T, this capital T parameter. And all that does is it gives us an ability to make that distribution, that probability distribution, softer, right, rather than hard at the top. So it gives us a much more flat probability distribution where suddenly the classes that aren't what we're predicting have more probability. So it's not changing whatever the maximum class is. You'll still get the correct output classification, but it's just giving more probability to those other classes. So this diagram is just illustrating standard neural network training, which I'm sure most of you are familiar with. And that is this is supervised training course, so we take our input, which also have labels. We push that through a neural network, which is trying to learn weights. We use a normal softmax, so temperature equals 1, to give us these predictions. And then we use cross entropy along with our labels, and we'll call those hard targets for a reason. They'll be obvious in a second. We train that with cross entropy loss typically. So this is just standard, neural network training, and we typically train that small model here in this case from random initialization. When it comes to distillation, what we do to change this is we try to use those soft labels that we're getting from our model. So those probabilities from our model that give us more rich information than the ground truth labels alone. And so this is going to look very complicated. You don't need to understand all this to understand our work. I just wanted to put the full thing there. So everything that's gray here is essentially what we had before. So standard neural network training. And then what we're doing on the side, so we do the standard neural network training where we have cross entropy loss and we're just using our ground truth labels. Alongside that, we do this distillation training side where we have this distillation loss and we use a softmax with a higher temperature than 1. Now, the temperature ranges you typically see will be anything from 2 to 10, essentially. 10 is a little bit more unusual, but in that sort of range, just to give you an idea for later. And what we do here is we use the soft predictions from our larger model, which has a better knowledge of how to distinguish these classes. And we use the soft predictions so that the probabilities, again, with a temperature greater than 1, from our student, which we're training. And we use this distillation loss, which is actually just KL divergence. So we're just comparing those distributions to decide how we should change the student and transfer some of that knowledge effectively. Now, in practice, we don't just use distillation loss alone. So even in the original paper, they use a mixture of the distillation and standard cross entropy losses to train. And so they have this weighting across the two, and that's what this alpha hyperparameter is. And we're not going to be looking at alpha hyperparameter, in the presentation, but we do look at it a bit in the paper. And in fact, there was a bit of existing work on looking at alpha and its effect on fairness. But the truth is that we don't actually change alpha very much in practice. And alpha is not as important as temperature when it comes to how distillation works in practice. Okay, so that brings us to a little bit closer to what the aim of this paper is, and that's looking at essentially how distillation affects fairness. But let me talk you through why we're looking at this first. So let's go back to this idea that neural networks are just functions. They just learn a function that maps an input, an input X to an output Y. Pretty straightforward. Now, when you think about this, when you think about how to compare models, you shouldn't just be thinking about how to compare aggregates. So aggregate metrics of how well they work, like accuracy. We need to be thinking about what the actual underlying functions that are learned are. And when we distill a large teacher model into a small student, as I've said, we tend to see that accuracy is maintained, right? So this aggregate measure of, for example, test accuracy, and all the metrics that we typically use to understand how good a model is are aggregates over your, say, test set or training set, if you're looking at, training accuracy or training loss. But typically we'd be looking at test loss or test accuracy, and that's just an aggregate over your entire data set, right? It's not talking about how it works for individual samples or individual classes. So is the fact that we see similar accuracy for the student as the teacher, does that imply that these two models have learned similar functions? And because of what I've already just explained, right, that this metric is an aggregate, that's not necessarily the case. In fact, it's probably not likely. Because how these models actually differ on individual samples, so individual data points, or on a more aggregate level for different classes can differ greatly and yet still have the same overall accuracy, right? So and this idea has been explored in other scenarios. So for example, pruning is a similar area where you often get, and an area of interest to me, but an area where you get similar accuracy, but you might not necessarily learn the exact same function. So the student and teacher can indeed learn different functions. And what we're going to be looking at is how different those functions are. But first, why does this matter? Why do we care about this? Sure, it seems academic, maybe they learn different functions, maybe they don't. Why does that matter to you sitting in the room today? So those differences between those functions are fundamentally how we understand the algorithmic bias of a model, right? So if a model predicts things differently, does it do it in a way that's uniformly different? Like, does it just for any type of class. So let's say we're talking about animals and ImageNet now, right? For all animals, does it change in the same way, or does it preferentially now classify cats better than dogs? Now that example is also not very motivating, and that maybe you don't care about how model classifies cats versus dogs, but you probably do care about a face recognition model at the airport being used to decide where you can get on the plane today or not, right? And it's the exact same thing, right? So when you take a model and distill it, the question is, how does its biases change from the teacher? And those can have a real world impact. In fact, they do every day. So let's come back to the paper now. This is what the motivation was for our paper. So having just gone through distillation and understanding that functions can be different despite aggregate measures of how good they are, we want to understand how does knowledge distillation, which is pervasive in its usage, affect fairness and bias. So these are some of the research questions that we wanted to ask. What classes are significantly affected by distillation? What is the impact of temperature specifically on those class biases? How does distillation and temperature affect group fairness? So I haven't introduced group fairness yet. We'll talk about that in a bit. And then related, but quite different, how does that affect individual fairness? So let's start off with class-based analysis. And this is relatively accessible, even if you're not familiar with bias or fairness, because all we're looking at here is how different are predictions on an individual sample basis for these two models. So here we use this measure called disagreement, and it's very intuitive. It's just the disagreement in the hard predictions of each of those models on individual samples. And we just count that essentially over your entire data set. So you take your test data set, for example, and then go over all of your samples, push them through both the teacher and student model, and count how many times they disagree. That's all this is, right? Now, if your models disagree, they are a different function by definition, right? You have a different output for a different input. That's a relatively simplistic way of looking at this. So that's the actual measure. And this measure, by the way, comes from this loss landscape perspective, which is a great paper in itself, but looking at something very different. Still trying to understand how functions differ, however. Now, if we just show you the class-wise disagreement over these two models, and remember that the student is distilled from the teacher, which is a much larger model, there's some confounding factors here that we have to try to separate out, right? So the most obvious one is that, sure, we've distilled the student based off the teacher, so maybe expect it to be similar to the teacher, but it is still a much smaller model. So if we see any differences, are those differences due to the model size, or are they due to the fact that we distilled it versus training it from scratch, right? And so for that reason, our common baseline across almost all these experiments is looking at how the class bias of that non-distilled student, we call it, but basically just a standard student architecture, so smaller model trained from scratch, trained from random initialization, how that differs from a teacher or from a distilled student, right? So that gives us a baseline that removes some of this uncertainty around, is it just model size that's affecting things, and how much of this is distillation? So here's the first figure of results, and this is relatively straightforward, but let me just explain it quickly. So here we're looking at two basic image data sets. So these are benchmark data sets. They're relatively small that I'm sure most of you have seen, especially CFAR10. So CFAR10 just has 10 classes. And SVHN is the street view house numbers. It also has 10 classes. CFAR10 is more general images, but very small. So it is things like images of planes and cats and dogs. Street view house numbers is actually just photos of house numbers. So plaques with the house number on the house. So it really is digits, but digits in the real world. So these are just very simple data sets to start off with, and we trained ResNet 56, so ResNet model that hopefully most of you are familiar with. And by the way, I want to say this because it's really important, but if you look at the ResNet papers, there are different models for CFAR10 versus ImageNet. You should use different ResNets for different data sets. It's a common, unfortunately, I think, tripping point for a lot of people. So we use the CFAR CFAR ResNet models for this. And what we do is we train this relatively large ResNet 56 on CFAR 10 and 100 and street view house numbers. And then we distill down to ResNet 20, which is much smaller. And on the side as a baseline, we also train ResNet 20 from scratch on these data sets. So what you're looking at on the left here is for CFAR 10, how the teacher, so on the very far left is how the teacher predictions per class. So that's why we have 10 classes on the X and Y axis for each of these boxes. How the teacher predictions differ compared to our student trained from scratch, so our small model trained from scratch. And then we see next to that how the teacher predictions differ compared to our distilled student, right, trained from scratch. And clearly, even in the case where you're training both these models from scratch, there are significant differences in how they predict samples from different classes. But we'll see that there's even more differences with distilled. So this doesn't tell us too much yet, but it starts to give you an idea of what's going on under the hood, is that we do see differences here in a class-wise disagreement manner. Now I'll just say, like, this is using temperature 9 and temperature 7, so we did explore this over ranges of temperatures, but this in itself doesn't give you too much information to go on yet. But I want to point out one thing before we move on, and that is that you'll notice here for CFAR 10, which is a little bit more intuitive, that really it's class 3 and 5 that seem to have the most problems, right? They're the ones that seem to be confused the most. And that's for good reason. That's basically cat and dog. So that example I gave before of a cat and dog, you know, being more similar than a plane shows up in real life. It is harder to distinguish a cat from a dog than distinguish a cat from an airplane, right? And that's intuitive. They have different features that you need to learn for an airplane, very different features. Whereas there are some shared features for a dog or cat. So this is where some of these differences or these biases come from, but not all, as we showed in the paper. So this is just a table showing like a more complete set of results. And what I want to point out here is that we did do these experiments at scale too. So I'll explain a bit more about this. But just first talk about data sets. So this was CFAR 100, which is essentially a small image data set with 100 different classes. And then ImageNet, which is a much larger image data set with 1,000 different classes. And we also use transformer-based models. We didn't just get CNN, so we used vision transformers here. And we distilled a large vision transformer to a smaller vision transformer on the very far right there. So the first line, you see the teacher test accuracy. And then NDS is the non-distilled student, in other words, a student trained from scratch, right? So you'll see they do have significantly different accuracies. And then below, we have all the distilled students with different temperatures. So these are students distilled from the teacher model. And what you see is consistent across all of these data sets, all of these models. Again, this is all images, but we'll talk about NLP in a bit, is that when we're comparing our student model, so up here, SC is trained student versus distilled student. So when we're looking at our distilled student from our teacher, this is the number of significantly affected classes by distillation. And we used essentially a hypothesis testing rule for this. So we see that we get relatively few significantly affected classes at low temperatures compared to the teacher. But as the temperature raises, we get more of these. And vice versa for the teacher model versus the, teacher versus distilled student. So I got this the wrong way around. I've just realized I was talking about TC. I should be talking about TC. So TC is the teacher versus the distilled student. So that's the one where you're seeing, like, as things go on, as temperature gets higher, our distilled student is actually more similar to our teacher. Whereas SC is the baseline where we're comparing just the student model distilled or trained from scratch. And I know that's a little bit confusing, which is why I just got myself confused saying it. But yeah, so this case, what we're seeing is that we get less similar to the teacher as we get higher temperatures. And this trend continues across all of these models and these two data sets, right? So you can clearly see SC essentially is going up and TC is going down relatively over all of these. So we thought that that's a bit more intuitive. And what you see here is there is accuracy, which can conflate with this. As I say, distillation typically gives you a similar generalization or similar test accuracy, but it does differ slightly. With CFAR 100, we see that the test accuracy doesn't have a clear, increasing pattern like we see in ImageNet. But even in ImageNet, that difference in test accuracy, I'll just point out, is relatively small. And it's especially small on the CFAR 100 side when you actually look at the scale on the side here. So what this is showing you is the number of significantly affected classes, compared to the teacher for the distilled student and compared to the student trained from scratch. And essentially what we're seeing is that in both of these cases, the number of affected classes goes down with higher temperatures. Okay, so there's clearly a straightforward, I shouldn't say straightforward, there's clearly a relationship between temperature with distillation and how these models are classifying things at a very basic level. And I'll just say that, like, when you go to very high temperatures, so remember that temperature softmax is modifying our distribution rate and making it softer. It doesn't make sense that this trend would continue, because you get to a point where you have a high enough temperature and you essentially get an almost flat probability distribution. So indeed, if you take the temperature up to extremes, which you never see in real life distillation scenarios, you'll see that this all starts going back down again. So that's just what this is showing them, is that there is a peak, essentially, where temperature stops helping things and starts hurting. Okay, this is not going to be very intuitive to you, and that's good, because it shouldn't be. This is not a great way to understand how we're affecting a model with distillation. Because even though we are showing clear differences, so clearly the learn function is different, right? We're classifying things differently. And we're showing that there are trends and how that happens with temperature. The fact is, just a change in your class bias alone, even though we use the word bias and we think it means bad things, which, you know, it typically does, in this scenario, class bias alone doesn't in itself mean anything. The fact that your class bias is changing versus the teacher doesn't necessarily mean something good or bad in itself. So how do we understand whether things are changing for the better or for the worse? That's where fairness comes in. So in order to understand what's going on in your model and how that affects outcomes, you have to understand a bit more about your outcome and who's involved in that outcome. So it does become application specific. And fairness is a whole field I don't have the time, unfortunately, to go over in detail, but I definitely recommend you to look at. But fairness, essentially, there are different metrics, many different metrics, in some cases, some of them conflicting, where we try to ensure that a model is fair. And in this case, this is group fairness. So what we're trying to do is ensure that an outcome is fair across groups. And when we talk about across groups, we mean groups with the same protected attribute, right? So in this case, a very simple example that always is presented is hiring and gender. And by the way, I am aware there are more than two genders. Unfortunately, this is just the way it's typically presented. Now, a real world scenario that has happened, unfortunately, multiple times is that people try to use AI for hiring. And if you do this in a relatively simplistic way, what you'll get is the result that's illustrated here, because historically there have been biases in hiring, right? And so a classic example of this was Amazon very early on tried to use machine learning to help their hiring. And they used their historic data of who they hired in interviewees, essentially, to train that system. And when they tested it out, it indeed preferred hiring men, despite qualifications. So these things happen in the real world, and that's why fairness is important, to actually understand what your models are doing and what they're doing with respect to these groups. So this is clearly an unfair outcome and an inequitable outcome and a bad outcome, right? I think almost anyone would say. So how do we measure that? And that's where these different metrics or different ideas of fairness come in, at least under group fairness. So the most simple one is this idea of demographic parity. And that's simply that if you have two groups of individuals and they have the same attribute, so in this case, it's gender. And so we have women and men here. If you have both those groups, they should have an equal probability of a positive outcome. And so what does that mean? In this scenario, that means that if we have a group of women and men, we would hope, and again, this is assuming that they're both qualified the same, we would hope that they would both be hired at the same rate or have the same probability of hiring. Now, we can't just use this statement here, this probability statement, that these two probabilities are equal alone to give us a metric that we can measure. And there are different metrics based off this idea. And the one we're going to be using, you don't have to understand too much, but it's demographic parity difference. And that's effectively looking at what's the group with the worst, essentially, or sorry, lowest probability of being hired, and what's the group with the largest probability of being hired, and how different is that, right? So the greater that difference, the more unfair our model. And if you have a perfectly fair model, you should get a DPD of 0, right? It should be exactly equal, and that should just cancel out. So equalized odds is another very common fairness metric, and we don't have too much time, so I'm not going to dive into detail on it too much, and it's a lot harder to explain. But effectively, you know, before I was saying, you know, we were assuming kind of that we had only qualified applicants we were choosing from. But in the real world, you have a hiring system where you have to decide where somebody's qualified, and then you have to decide who you're going to hire. And those two things can be, you know, different. But what we hope in that situation is that of the qualified individuals, we're hiring the same frequency of people, essentially, the same number, not numbered, but the same amount of people. So I won't go too much into this, but in this case, we add the extra attribute of essentially qualified, and we consider that along with both positive and negative outcomes, it turns out. So this is a much, much harder fairness metric to satisfy in the real world, but it is, most people would consider a more fair metric. But when I say that, it always depends on your applications. There are applications where equalized odds make sense. There are applications where, DPD makes sense as well. So I'm just going to go over this quickly, but that's a very quick crash course into what these fairness metrics are. Now, again, for EOD as well, we use a different metric. We can't use a statement alone. So we use this metric called Equalized Odds Difference. And similarly to DPD, Equalized Odds Difference of 0 means perfectly fair. Okay, what datasets do we use? And you know what? When it comes to datasets, fairness is difficult because there aren't that many datasets. And as you can imagine, what we're trying to deal with are often, sensitive attributes. So things like gender and age and race. And that there aren't too many datasets on. And what the fairness community has relied on a lot, actually, is this CelebA dataset, which is honestly super weird. It's quite problematic in many ways. The nice thing about it is it does have all these images of people. It does have things like gender and age. Unfortunately, gender is binary in this, I'll point out. But gender and age, and I don't know how they've annotated the age. Hopefully, they've actually looked it up. But they're all celebrities, so presumably you could actually figure out their real age in the images. And then it also has these kind of benign attributes like, are they smiling or are they not smiling? Or are they wearing glasses or are they not wearing glasses? And so the reason this is nice for fairness is that we have these protected attributes of gender and age and race and so on, which we hope not to be biasing our predictions based on. And we can predict things like smiling or glasses, right? Where it's clear that we shouldn't be considering somebody's gender or age or anything else that's protected in determining whether they are wearing glasses or smiling. Now, by the way, I've been even looking at these examples, which are literally from the website for this dataset. It's very obvious that this is a problematic dataset. So yeah, one of the issues in, I think, the fairness community is having access to good datasets for this still. Now, fairness is a much more comprehensive and interesting thing to be looking at. And so we go back to our analysis of trying to understand how distillation affects, an application where this fairness metric makes sense. And so we first run this with ResNet 50, which is a much larger model for larger images. And that ResNet 50 is our training model, so our trained teacher model. And we use ResNet 18 as our student model. So we distill ResNet 18 from ResNet 50 to give us our distilled student. And then we also train ResNet 18 from scratch to give us our non-distilled student. So that's what's plotted down here. Now for the protected attributes, we used age and gender. So I'm showing both of those here. So the top one is age and the bottom one is gender. And then we evaluate this on smiling. We also did this on glasses. That's also in the paper, but I'm just not going to show in the presentation because it's very, very similar. So this is a classifier based on ResNet 50 or ResNet 18 that's classifying whether an image of a person is smiling or not. And indeed, you do see differences, between these protected attributes of age and gender for the teacher and the students. The question is how that changes over time and what are those differences relative to a teacher. So I'll just point out again that what you want is an EOD or DPD of 0, right? That's what we always want. Of course, we're very far from that. What you notice over time, so these horizontal lines are essentially the teacher. That's why they're fixed. So this is the teacher's fairness. And in particular, these two up here are essentially DPD, and the ones down here are EOD. So these two different fairness metrics are essentially these two groups of lines. And now the purple lines are effectively showing you what happens to our distilled student, right? So the student that we're distilling from a teacher as we increase temperature and what happens to its fairness. And there's a clear trend in both of these where you see that the fairness improves, right? So it's decreasing with higher temperatures, and that means that our model is becoming more fair. So I'll refer to the bottom one first because there's some other interesting things to look at. But here we see that we go from a fairness that's very close to essentially, where is it down here? Our non-distilled student. So our student with a low temperature is learning something close to our non-distilled student. And then at very high temperatures, we actually get closer to the teacher fairness. which is much better, right? It's much lower. So clearly temperature is affecting, in an intuitive way, how close you are to what a student trained from scratch would be in fairness. So that's this red line. To a teacher, which remember is a much larger model, and presumably that is why it can do better at fairness. It can learn more salient features rather than overfitting. Sorry, not overfitting, but more salient features. And we see that we get closer to that teacher's fairness with higher temperatures. Now, what's interesting is up here, so this is looking at EOD. When we look at DPD up here for CelebA and Young, we actually see that we can surpass the teacher's fairness, right? So our student model, which you remember is much smaller with very high temperatures, can actually surpass the fairness of the teacher model. So this was a surprising result. I don't think we were expecting to surpass the fairness of the teacher model, but it's a really, really interesting future direction of can you use distillation to improve fairness? But we don't go there in the paper. And so you'll see at the bottom, in this particular case, it happens with both of these fairness attributes, right? So it's not just restricted to one fairness attribute alone, but it does vary. Sometimes you don't beat it, sometimes you do. So by the way, if there are any questions, I'll probably leave it to the end, but yeah, hopefully this is clear to anyone in the meantime. So this is a table of the results. And indeed, we see like the best fairness in both of these. So in this one, sorry, is when you have a distilled student with a high temperature compared to the teacher and the non-distilled student. So that's really, really interesting. So in fact, in some ways, distillation at high temperatures may improve things, but overall, I would say, distillation is not typically used with a temperature of 10, by the way. It's typically used with much lower temperatures. So the models you're seeing in the real world probably are using distillation temperatures from 2 to 7. And in that case, what you're seeing is a student that's distilled from a teacher and is less fair, right? And that's a problem. So I think a clear result of this analysis, and we'll see more results that verify this hypothesis, is that we should be looking at this when we distill models. Because yes, in some extreme cases it can help, but most of the time you're going to have a model with reduced fairness, and that's a problem. So again, I just want to point out that, going up to temperature 10, sure, we see this improvement in fairness, but the more you increase your temperature, you get to a point where it's a bad thing. And so this is just a log scale essentially showing that over time, sorry, not quite, it's not log scale. It's a scale where we're missing some of the samples at higher temperatures because we just sampled more coarsely at that point, but showing essentially that you go back up to having just the same fairness as the original student trained from scratch. Right, so there's obviously a sweet point in terms of temperatures where this is maximally helpful for fairness. Now, that's all well and great, but we're really just looking at computer vision and images. And as you all know, people care about things other than images. So we also want to look at text. Now, it turns out there are actually relatively good data sets for text. They come from horrible places. And I'm not going to show examples of the text because it's really horrible. But essentially, there are data sets, and this is a particular data set called HateXplain, that look at trying to understand essentially offensive and hate speech online, which unfortunately is not uncommon. And this data set tries to separate out these different samples. And a lot of this was from Twitter and Gab. I'm actually not sure what Gab is, but Twitter I think we're all familiar with. A lot of these are looking at Twitter and essentially trying to separate these into different target groups or different sensitive attributes effectively. Based on different things like race or religion or gender and so on. And they would label these as hateful, offensive, normal, or undecided. Now, for our purposes, we essentially lob together hateful and offensive under toxic, and then compare toxic to normal. And what we're trying to understand is how being in one of these sensitive, protected attributes, and we just use them on these general target groups of race, religion, gender, and so on, how having one of those protected attributes would affect the classification of it being toxic or normal. Because this is an important thing in the real world, right? Like most companies, at least until recently, cared about moderating their content and checking that you're not allowing this content to persist on the internet. And it's a difficult problem. So in this case, we use BERT. So BERT is a fairly well-known, I think, transformer-based model for encoding language. And we used another model called DistillBERT. DistillBERT, despite the name, isn't itself distilled necessarily. it's an architecture on BERT that is much smaller and was designed for distilling too. So just a subtle terminology difference there. But yeah, so we distill BERT essentially to distill BERT, and we do the same thing where we also train distill BERT's architecture from scratch, and we compare things there. And again, we see the same pattern, right? Where we see that, you know, at low temperatures, you end up with a fairness that's very close to what a student trained from scratch would be. And at high temperatures, we get close to or surpass our teacher's fairness. And at very high temperatures, again, things regress, right? So basically the same pattern. And remember, this is very different models, very different tasks, very different data modality, right? So this is now text, which I think is really interesting. Okay, so any questions before we move on? Otherwise, I'll wait till the end. Okay, let's, oh, yeah, maybe there was. No, okay, let's move on to individual fairness then. What happened to that slide? Yeah, so we've talked about group fairness, and group fairness is probably the most common setting for analyzing fairness of models. And it has, the reason it's most common is because it is very well motivated in terms of actually law, right? So in many countries, there are laws specifically protecting people with various protected attributes and how they should be treated. So it's very well motivated that way. There's another type of metric or group of metrics which are very different, and they're called individual fairness metrics. And what these propose is that rather than, you know, group fairness was about treating individuals with the same, with different protected attributes, so different genders, for example, treating them the same, right? That's a very intuitive way of being fair. Individual fairness is a bit more subtle. Individual fairness is that the concept that similar individuals should see similar outcomes. So at first that might sound the same, but it's actually not the same at all. So sure, similar individuals will not have, you know, different protected attributes, but also this is similar individuals on a very basic level. Similar inputs effectively is what this is saying. So on the right, I have an example where X1 is close to being X2 under some metric. And if that's the case, what we would expect under individual fairness is that they would have similar outcomes as well. So you'd expect the outcome of, this is mislabeled, this should be Y1. The outcome from X1 should be similar to the outcome from X2. So that's the basic intuition as to what we're trying to seek here. So for a semantically similar input, which is obviously very dependent on a data set type and application, we expect to see a similar output at an individual level, right? So that's really an individual sample level. So it's easy to think about this as individual people being samples, but they don't necessarily have to be people. And in this analysis, we used a specific, well, one of the most popular individual fairness metrics proposed by Dwork et al. in 2012. So this was, again, U of T work. And we looked at this across images as well. So I didn't explain Trifeature. Well, this was a synthetic data set that we used in images basically to show that this whole relationship wasn't just due to simple feature differences in learning features, essentially, like we talked about with cat and dog versus airplane. Anyway, but in terms of CelebA and HateXplain, which we did see, so same data set, same models, but different fairness metric now, this individual fairness metric. And again, this is a metric such that you want to see very low being fair. So 0 should be fair effectively. What we see is that our non-distilled students, or students trained from scratch, tend to have much higher, in other words, less fair outcomes than the teachers themselves. Whereas when we distill a model, we see that we get much better outcomes in terms of fairness, right? So very similar again, that with high temperatures, we tend to see more fair models. So I'll just conclude this now. What we've shown is that, well, first, actually, I just want to go back to the motivation, because I don't know if you're all familiar with how pervasive knowledge distillation is. Like, I am very confident saying that you are affected by the decisions of a distilled model, not just daily, but many times per day. The fact is, most of the models running on your phone, so if you have an iPhone, for example, you know, Face ID is very likely to be a distilled model. If you have an Android phone, you're not safe either, because, you know, all of those functions that are cool, like anything in Google Photos or camera, is very likely to be distilled models as well. So all these models, and then all the models that you don't see in the cloud, right, that affect things like your credit score, or as we talked about, like being able to get on your plane and so on. All of these models many of them are likely to be distilled because it's just cheaper to run them, and in some cases enables their mobile usage, for example. So this is very pervasive, and yet somehow we are the first people to look at the effect of temperature on fairness, as far as I'm aware. And what we found was quite consistent across different models, very different models in terms of size and architecture. So we saw this across CNNs and transformers for both vision and language. We saw that distillation temperature does, in fact, affect the fairness of models quite consistently. And we found that consistently higher distillation temperatures, up to a certain value at least, because at some very high temperatures it decreases. But in general, higher distillation temperatures within a narrow range of typical temperatures used leads to more fair models. And what we also saw was that in some cases, our distilled student models, which again are much smaller models than the teacher, can actually be more fair than the original teacher model at high temperatures. So where can you go with this? Well, I mean, obvious direction is kind of, can you affect improving model fairness with distillation? And even though we seem to see better results in some of our work here, I wouldn't conclusively say that we've shown that yet, for sure. Are there other trade-offs to using large temperatures? So yes, in fairness, that's good. But as we even saw some of the plots, like that can affect your accuracy as well. So you have to consider the trade-offs between different things with high temperatures as well in an actual application. Where we didn't look, because it's a little bit more difficult, is does this have the similar effect in LLMs? But we did look at transform architectures on smaller text data sets. So I'm pretty confident in saying that's likely, even though it's very pervasively used. Okay, and I'll just finish there. And again, just to mention, this is Ida's work. Ida just defended her master's, and she's actually looking for work now. She's in Toronto, so not much closer to Windsor than Calgary anyway. But yeah, so if anyone's got interesting opportunities and you want Ida, and she's a great student on all this stuff, really excellent engineer, just contact me and I'll share her details. This paper is on TMLR. As I said, we have uploaded camera ready. It should officially be published within the month. But yeah, so I'll leave it there. And any questions?
Yeah, so any questions?
Hello.
Hello.
Okay. So I'm not an expert in this field, but I have a pretty straightforward question. That is, since knowledge distillation transfer knowledge from a teacher to a student model, so is there any evidence that biases got amplified or increased during the process of, in this process?
In the process, did you say feature distillation or knowledge distillation?
Knowledge distillation.
Okay, yeah, I mean, that's what we're showing essentially, right? Is that yes, there is, unless I'm misunderstanding your question, what we showed in this paper is that there's a significant effect of distillation on fairness on that student model where you've transferred knowledge using distillation.
Okay.
Any questions? I have a quick question. So you mentioned about so the student model is essentially a smaller version of the teacher one, right? When we actually use the distillation process and reduce to a smaller model, the size of the reduction in model, does that also in any way introduce any kind of issues like the one that you showed? Anything we know about?
Sorry, when you say issues, could you be a bit more
specific? I mean, let's say it can be fairness issues or model performance. How much we can reduce effectively? Is there anything?
Oh, how much can you reduce the size? Yeah, I mean, this is very empirical in practice, how much you can reduce the size. But like in many of the cases, I did have specific numbers on the slides I could go back to, perhaps, to give you some examples. So the important thing with knowledge distillation is generally you want to try to keep the same architecture. So you'll see in many of our examples, not all of them, but most of them, we used a much smaller version of the same architecture. So what does that mean? It typically means it might be a shallower architecture of the same type. So for example, a ResNet with fewer layers, it might be narrower, so it might not have the same layer width, and so on. So preserving architecture seems to help with distillation. But aside from that, you can go down quite a bit. So let me give some examples from ours, and I don't think these are the best distillation results ever. But let me just go here. So ResNet 50 was 24 million parameters to ResNet 18. And so this is a very, I think, easy distillation scenario. And you go down to, basically half the parameters here. If we go to HateXplain, so HateXplain and Bert, I did write down the numbers at the top here. So we go from, yeah, exactly. Now, I think we just did that, but in practice, if you're in industry, what you do is you try to go down as small as possible while maintaining, whatever metric you care about. And I wouldn't say in general that's fairness, obviously, because it seems like people haven't considered this very much. But typically they'll be to do with the performance of the model, right? So it is very effective. Perhaps the most extreme case of it, actually, now I think about it, is in one of my first slides, and that's how it's being used with LLMs. Sorry, let me just flipping a little bit too much through slides, but I want to show this all the way back at the top here. And so these are parameter counts here, right? So we've gone from 671 billion parameters to 1.5 in the lowest case for DeepSeek. And that is clearly affecting performance to some degree, but each of these distilled models, by the way, I should say, the reason they have so many distilled models is that these ones have different strengths. So they'll be good at different tasks. And so that's what they're showing this table. And I'll refer you to the technical report for more details. But essentially, yeah, they're taking this clearly crazy massive model and distilling it down to, what is that? Essentially 1%, not quite 1%, but a very small model compared to the original that is still effective. And even, for the 70 billion, that's still very small compared to 671 billion. And I haven't got the stats on Gemma. Gemma, I think, is probably even more extreme from what I've heard. So Gemma 3, sorry, which is the latest Google model. So yeah, it's very effective in practice, which is why it is so pervasive in usage. And it does have other, even if you're not looking at, making a model smaller, so that's what I'm focusing on because it's the most common use case. Distillation is often used to make your model better. So for a model the same size, it can improve the performance of the model in terms of generalization, just because you're suddenly, using that soft knowledge or essentially label smoothing in effect with distillation. So you're using more information than just the hard labels to train with. Yeah, definitely recommend looking into distillation. I think it's been very popular with CNNs historically, obviously, and in that era when that was the craze, it was very well known. And I think until recently, where LLM started using it a lot more outside in academia, it wasn't as focused on, but it's seeing a lot more focus now. But in industry, it's just been pervasive, ever since deep learning, essentially.
Thank you. Any questions before? Okay, so thank you again, Dr. Yani. It's very nice to meet you, and it was a very exciting talk. Okay, so.
Great. Thank you very much, everyone.